Boa tarde a todos. Vamos dar início a mais um seminário da série de seminários do INCT Icon IoT, ou Icon IoT, o INCT de Redes de Comunicação e Internet das Coisas Inteligentes. INCT é o Instituto Nacional de Ciência e Tecnologia, promovido pelo CNPq, CAPES. E esse INCT, particularmente, ele tem membros do Brasil inteiro, tanto pesquisadores quanto instituições, então temos uma abrangência bem grande. Hoje teremos um seminário internacional, e por isso que estamos num horário diferente, né, às 13 horas em vez das 16, e por isso eu vou mudar agora para inglês para iniciar, então, o nosso seminário. So, good afternoon, everyone. Thank you for joining us in this seminar of our National Institute of Science and Technology for Communication Networks and Internet of Things. And today, in our series of seminars, we'll have the pleasure to have here Professor Fabrizio Granelli from the University of Trento in Italy. And the seminar is called Network Digital Twins in Future Networks, from Theory to Practice. Professor Granelli is full professor at the University of Trento, a visiting professor of the State University of Campinas, Unicamp, and the University of Tokyo in Japan. He has 26 years of experience in the IEEE Communication Society, the ComSoc, as distinguished lecturer, director of online content, director for educational services, and director for conference development. Professor Granelli was general or TPC chair of several prestigious IEEE conferences, including IEEE GlobalCon and NFV SDN and others. So he was an associate editor-in-chief of IEEE Communication Services and Tutorials, and currently senior editor of the IEEE Transactions on Green Communications and Networking. He is the author of more than 300 papers on communications and networking topics. So, Professor Fabrizio, once more, thank you for joining us here, and feel free to start your seminar. Thank you.
Thank you very much. It's an honor to be here speaking in front of you, and also my pleasure, because I like a lot to discuss about this topic that I think is very interesting in these modern days and for future networks. So if you will have any questions, we will leave some time for Q&A at the end of the presentation, but also feel free, if you wish, to contact me offline. Here is the email, fabrizio.granelli@unitn.it, if you need more information or if you wish to discuss with me later on. So the topic of today is to discuss about a novel concept that is network digital twins, and it's a topic that received quite a lot of attention, but most of the words in the literature are theoretical or let's say based more on modeling, and rather they don't arrive up to the actual implementation. So what I will try to do in this webinar is I will try to discuss, first of all, why network digital twins can be important, and then I will try to provide you some examples of what we are doing in my research group related to implementing network digital twins in real systems. So I will start just with the last part of the title, so future networks, because I wanted to stress out that, of course, networks, especially mobile networks, are evolving very fast and are becoming the dominant technology to get access to the internet, all the online services. And this is due to the fact that they are, in a very quick way, covering a lot of useful KPIs for services like data rate, reliability, latency, and so on and so forth. However, starting from 5G, also the architecture of mobile networks followed a very important revolution, becoming more and more softwareized and flexible and capable of better adapting to the needs of the users and to the needs of the services. And today we are almost in the middle between the fifth and the sixth generation of mobile networks. And while the fifth generation can be described by the triangular diagram in the center of this graph, where there are the three main applications: enhanced mobile broadband, massive machine-type communication, and ultra-reliable low-latency communications. This triangular structure is becoming an hexagon in 6G because of the introduction of new technologies and new approaches. And those are integrated sensing and communication, AI and communication, and ubiquitous connectivity that are becoming the focus for the next generation. What is important is that, as I will try to show you later on, the network digital twin is useful for a lot of applications in networks, but especially it targets quite well this AI and communication topic. So I believe that in 6G there will be space already for seeing examples of network digital twins, and that is why it's important to know what it is and how to develop effective network digital twins. First of all, let me take one step backwards and say, what is a digital twin? Because there is an important aspect. Digital twins are existing already in several applications, especially manufacturing, for example. And what they provide is, of course, a representation of some real object or a real device. But what is specific of the digital twin is the fact that this digital version of the real object is characterized by accurate encryption, in the sense that the digital twin is always, ideally, a precise replica of the physical twin. And these are real-time updates or time flow between physical and digital twin, so that when I look at the digital twin, I get a full picture and an up-to-date picture of what the physical twin is doing, what is happening, what is the state. So this concept is very important, because besides using the digital twin simply as a digital model of the real system, we have also the characteristics that the digital twin gathers a lot of data from the real system, and thus allows to support also analytic tools that can analyze and provide more insights in the physical entity, directly looking at its digital version. As I mentioned, there are several applications already quite popular, like manufacturing, supply chain, constructions, but also a more advanced application of digital twins, for example, in healthcare. You know, healthcare requires to be very specific to the human body, to the specifics of the person. So there are works towards defining the digital twin of a person, so that we can have personalized treatment, for example. But also we have digital twins in complex systems, like system of systems, like a smart city, because we want to aggregate traffic, data traffic from several sensors for monitoring the state and understanding what's happening. If we apply this to the networks, what we achieve is a network digital twin. And also, again, in the network digital twin, the most important aspect that distinguishes a digital twin from a simple simulator is the fact that there is this continuous connection between the physical and the digital version of our network in this case. So why is it interesting to design network digital twins? In networks, we have at the moment a very lively situation, because there is a lot of exciting topics that are emerging. But there are also, let's say, modern trends and big trends that are followed for networking innovations, and they go towards softwareization of networks, automation especially to reduce costs, introducing AI and machine learning in networks, and also sustainability. And for all those four trends, the digital twin can provide, of course, not the only solution, but it can provide one of the tools that are required to handle the complexity of those goals. Because, for example, we can use a network digital twin for analyzing scenarios, so we can evaluate potential changes in the real system without operating them directly on the real system, so that we can study different alternatives before implementing them. We can handle heterogeneity, so it's possible to handle different components with different characteristics. It's possible to provide predictive capabilities, because I will show you in digital twins we can predict somehow the future using our digital version of the networks. And especially we can achieve self-awareness, because we can build like a mirror version of the real network that we can use for aggregating the traffic and enabling to better understand the state of the network in real time. So the applications of network digital twins are mostly, in my opinion, in the network management area. So we can use them for proactive maintenance, for performance monitoring, demand forecasting, predictive analytics, anomaly detection, and so on and so forth. So let me give you some examples of application of network digital twins. The first one that I selected is applying network digital twins in 6G, of course, because I started with that as motivation for this work. So how can we apply a network digital twin? How can we integrate the network digital twin within a mobile network? Well, it's a sort of complicated. So here there is, I could speak for 1 hour just to explain you this, but if you want to simplify, this is the management structure that we developed for providing network security in 6G against attacks, against security threats. And if you look, there are big functionalities that are required. So we need, of course, to be able to acquire the data to perform attack detection, for example, in the real context. That is quite typical application of machine learning, for example. And then if we want automation, we need also to provide an automated recommendation system that will select which are the mitigation actions that are to be implemented in the execution phase on the physical infrastructure. Here, if we want, we can introduce the network digital twin in this purple box in the bottom, in the center, because it's possible to use the network digital twin in two scenarios. One is using the digital twin to perform predictions, so to use the digital replica of the network in order to understand what might happen, whether there are threats that are growing in the network. And on the other side, I can use the digital twin also for impact analysis. So I can check whether the mitigation actions that are proposed by the recommendation engine are suitable and whether they generate the best and the desired effect before implementing them on the real network. So somehow, one of the most straightforward applications of the digital twin is to provide a sandbox where the network management functions can play and they can learn what might happen in the real system, whether in the future or as a result of additional control actions. Here there is an example just to explain a little better what we mean. If you look at the diagram on the bottom right, there is in red how the network digital twins that here are in the sandbox component of the system, in this SAN, how they operate. So one way for the digital twin to operate is to receive data from the infrastructure and to perform attack prediction. So it can the network digital twin can continuously loop, make estimates about the near future, and maybe detect the growing possibility of a security threat, so that it can be even mitigated before it fully happens. On the other side, if you look in the bottom, I can use the digital twin in the impact analysis mode, where another engine of the network management of the mobile network will ask for the analysis of what-if scenarios, so that I can test different scenarios of solutions, of mitigations to solve security problems, and I can evaluate the corresponding estimated impact, so that at the end, the actions are applied here at the very bottom of the figure only when we are sure that those are the most appropriate for, and at least the ones that operate the best in the digital version, in the digital replica of our network. And here there is just a little bit better vision to remind about the loop. So we have data collection, we have the threat prediction, where we use, in this case, the digital twin, so in the purple in the middle. Then we use the digital twin both for predicting and generating recommendations before attacks can happen, but also for analyzing the potential impact of different recommendations before executing the corresponding decisions. And how did we build this digital twin? In this case, we use a network emulator that is based on Mininet, for those of you that are familiar with SDN emulation. It's publicly available, the engine of the digital twin. And why we selected this is also important, because we wanted to have a tool that was capable of being programmable and be reconfigurable in real time. And that is why we wanted, and we decided to use a software-defined network engine for managing the network. But also we wanted to be able to replicate the flexibility, the adaptability to the services and to the user's demand. And this is done by implementing also network function virtualization on top of the SDN network, in order to make simple to migrate services and deploy services in order to replicate what is happening in the real network. In this case, the problem is to keep the digital twin synchronized with the physical twin. So here, of course, the problem is complicated, because there are delays that now I don't have time to get into the detail, but just to make the story short, what we decided to do is to periodically collect data from the physical twin, to send it to the digital twin, but also to predict the near future, so that it is possible to roll back the time in the digital twin and reduce the playback delay, so to reduce the time between having the real data in the real network and reproducing it in the digital twin. Every time we receive new fresh data, because we might diverge in the prediction from the real network, we implement, in this case, a simple controller, a PID controller. So what we do is we continuously estimate the new state and the future state of the digital twin, and every time we receive fresh data, which is up to date from the physical twin, we run this loop where the PID controller helps us to maintain the predictions aligned as much as possible to the real data that is coming from the physical twin. Here, there are a few examples to show you that depending on how far you look in the past, you have different error values. Of course, you get a more precise estimation if you look, let's say, relatively for a long time in the past, like here in this case is 5 minutes. And on the right part instead, here there is the forecast horizon, so how far we can look in the future. For example, we can look 5 minutes more in the future or 10 minutes more in the future. Of course, the longer we make the estimate, the higher will be the error value, because we will not be able maybe to capture all the oscillations of the traffic. But what is important is that if we correct using the PID controller continuously our estimate with new data coming from the physical twin, you see the impact on the accuracy, because on the left there is the prediction without the correction that tends to diverge, and then in blue on the right part we have the corresponding error when we continuously or periodically, more precisely, we periodically correct our predictions based on the real data. And of course here it shows that we get much higher accuracy because of the real-time flow from the physical to the digital twin. Another interesting application of the digital twin is more transversal. For example, if we want to study energy efficiency. Energy efficiency is a complex problem, and it's especially important, in my opinion, if we use edge computing, so if we do MEC, because MEC represents a technology that brings the data nearer to the users, but also the processing power nearer to the users, near to the edge of the network. And this makes this technology extremely pervasive, but also globally energy demanding, because we need to have a lot of new computational power units that are spread near to the users. And if we want to be efficient in handling this kind of networks, we have a lot of problems because hardware and software are heterogeneous. We don't know exactly which virtualization we are going to use for the service migration components. And of course, energy consumption depends also on the specific hardware that we use, because the hardware will impact on computation, storage, and also communication performance. So how can we study this system? How can we trigger the correct resource allocation strategy if we want to be energy efficient? What we did is we built, of course, a digital twin of this kind of network. This is only a simple diagram where the edge basically is the node that you see in the middle. So we generated, let's say, an additional set of nodes on the edge of the network near to the base stations where we could deploy services, and we could deploy also network functions coming from 5G, like the user plane function, for example, that is the switching node in 5G. And what we did is this time we tried to replicate also the computational capability in the network digital twin that we built. So we limited the processing power of the different nodes corresponding to some real benchmarks that we run on real systems. For example, here we assume to use a Raspberry Pi Model 3, and here there is a diagram that shows how we selected in red the proper amount of operations per second to provide to that container in order to represent the real physical system. And just with that, without considering energy, we could study the trade-off, for example, between the CPU usage and the throughput that we can achieve, because we are resource limited. So if we switch a lot of traffic, we reduce the computational power. If we compute a lot, so if we move a lot of computational power to the edge, for sure we will reduce the switching capability of the node, because the total power is limited. And here it shows, for example, that there is a region in light blue that it's not available, because we cannot have at the same time the maximum CPU usage, for example, and the maximum network capacity available, or we cannot have more than a given amount of processing allocated to the switching node rather than to the computation. But what we did is we built a real testbed, and the real testbed was built with different virtualization strategies like bare metal, virtual machine containers, but also provided by smart plugs, so that we could measure in real time what was the amount of power consumed by the whole node, by an entire edge node. And what we did is we ran different experiments, different benchmarks, and we could build in this case, the digital twin in form of a 3D surface, a 3D response surface, showing the impact of the data rate and the CPU utilization in terms of energy consumption. So here you can see 3 diagrams that represent which is the performance in terms of energy consumption of bare metal strategies, containers, and virtual machines, depending on data rate and CPU utilization. And you see that they are clearly quite different one from the other. However, we wanted to do this in the most real-time manner. So we didn't want to run several experiments offline, because typically your devices will be on and they will be operating. So we cannot play with dumb traffic or, let's say, non-user traffic just to get some information. So what we did is we resetted these models and we built the models runtime by acquiring the measurement points from the real system while it was running. So here you can see we introduced a few machine learning solutions in order to perform the same action to build the response surface, but from time to time, whenever like 10 points more were collected. And you can see that while at the beginning on the left, the estimate is very bad, after a while the surface response were estimated in a relatively precise way. So this shows how you can build the digital twin, let's say runtime, while the system is running. Then you will ask, but how can we use it? We can use it in a closed loop like this. So we can use it for performing service placement, for example. So we can use the digital twin of the network if we want to do energy efficient service placement on the edge of the network. And in this case, even with very simple approaches, the performance is really impressive because it's very well tuned to the real system. For example, here I show you a very simple example, a comparison between optimal allocation, which was done by brute force exhaustive search, random allocation, where we would allocate tasks randomly on the edge, and random allocation filtered by the digital twin. So in the third case, we use the digital twin to check in which cases the digital twin would estimate that random allocation was consistent with the quality of service requirements of the applications. And the results are quite interesting, because if you look at the bottom, you get basically roughly half of the power consumption, just using the digital twin as a reference, with basically a QoS compliance rate that is almost perfect. While in the random access, the performance is of course lower because of the errors that are done. So this shows that the self-awareness that comes from network digital twin is very important, because it allows us to take informed decisions and to make automated decisions too. Another thing that you can do is what I call a physical level network digital twin. In this case, the idea is to build a replica of the propagation of the signal. So here you can see a very simple example that we built in the area behind the university, where the colors represent the quality of the signal. So in this case, the antenna is, as you can see in the middle of the video, and you can see the propagation pattern across the suburb where there is the university. Why this can be useful? First of all, let me explain you how it works. So it's a combination, the system is a combination of OpenStreetMap or Google Maps to get the 3D maps of the area. Then we use a modeling and rendering software like Blender, for example, for reconstructing the 3D scenery. Then we use a ray tracing software. In this case, we used freely available software from NVIDIA. And finally, we build the coverage map that you see on the right part. So you start from selecting the area that you want to study. you build the 3D area. This is the downtown of Trento. And then you position your base stations, and you can analyze an approximation of the coverage patterns across your city, for example. However, this is not a digital twin yet, because this is a simulation. In order to build a digital twin, what we did is I sent students around the city, and I gave them a software on the cell phones to analyze the RSSI, so the received power, so that we could have real data. And you can see on the diagrams on the left or on the right which are the samples on the left with respect to the estimated values that are in the ideal would be that red dotted line. And in the map, you can see in different colors the difference between the measured value and the estimated value. Once we have real data, then we can build a digital twin, because now I can use the measured data. Here we did a very simple compensation using a sort of Gaussian error propagation, and we corrected the values of the coverage by using the real values, so that we could have a more precise version of the coverage. So now we have one possible, let's say, digital twin of the physical layer, because now we are able to estimate with a higher level of accuracy the received power in all the areas of the city. And for example, here the application is we were interested in studying drone usage in the city. So here it shows you the ray tracing that provides all the echoes of the signal to the drone while it's moving around a base station. And of course, this kind of solution can have a lot of applications in planning, even in real time, in mission planning of drones, in planning of networks, or all the cases where we have self-organizing networks, or we need to have dynamic reconfiguration of antennas, for example. Here there are a few examples where we augmented the digital twin by including these red dots that are UAVs, so drones, bringing connectivity in hotspots. So you can see different examples where we included artificial components in the digital twin in order to study hypotheses and hypothetical scenarios of coverage. And finally, this is a little bit not exactly a digital twin. This will be not a network digital twin, but more a digital twin concept, or if you want, a combination of digital twins. We can use digital twins also for augmenting datasets. This is very important because today machine learning and artificial intelligence approaches are very hungry of data. They want a lot of data. They require a lot of data to provide good models and to learn properly. So what we did here is we started, as an example, with a very well-known data set that was built in Stanford. That was a set of videos that you see now on the right, taken from a drone on top of a crossing area. And we rebuilt the same scene in 3D using a similar approach as before. As you can see here, you have the model. Why did we do this? We did this because we wanted to increase the amount of data that we had for training AI, because as you can see, we can replicate some existing trajectories of people in the area, but you will see now in a few seconds that we can also increase the number of people. This is complicated because typically you don't have a lot of control in the area that you are acquiring the video. And also, by the way, you can have a lot of problems with privacy. Here you can see we can add 100 agents, 1,000 agents, and we can really replicate in a very realistic way, because we have a real 3D version of the area. And also, if you see, we have very precise models of the behavior of the people. This is another feature that we had. But also we can also completely change the view that we have on the system. All the Stanford dataset was taken from on top. Here instead you can look at what happens from a different angle, so that you can train your system even in angles that your real camera couldn't acquire the information. Also because, by the way, if you for privacy reasons, you cannot use, of course, a video of a person easily. So in this case, they are all synthetic humans, so we can use them as much as we want. So a few more words of considerations taken from those examples. The last example showed you the possibility also to combine digital twins, because there we had the 3D replica of the area. That was the digital twin, let's say, of the scenario, but also the 3D digital twin of each of the persons. So we combined digital twins that were people digital twins and scenario digital twins in a network of digital twins. So this is not computer networks, but it's still a network where we want to interconnect different digital twins. That is a very important aspect, because up to today, and this will be probably common even in the future, it's not very simple to define the boundaries of the digital twin itself, because it can be an object, it can be a collection of objects, it can be a complete system of systems. So these digital twins sometimes can be single, sometimes can be a combination, especially when you are mixing interdisciplinary aspects. For example, if I mix the digital twin of a renewable power source with a digital twin of a network, I achieve something that is very difficult in reality, because if I can enable them to speak together, I will have the capability both to study the energy patterns, the consumption and the energy provisioning, as well as the network performance, all with the same system. So I believe that even though now it's not yet available, in the future we will have networks of digital twins. And some researchers are already speaking boldly, let's say, of the internet of digital twins, because maybe in the future digital twins will be like web services that we can combine together to analyze more complex tasks. So this will be probably one of the lines that will be covered in the next years. At the moment, just a few exploratory works are available. But another point in digital twins is also who should be the owner or the producer of the digital twin, because today, basically, the examples that I presented you were built from my research group. So they were based on open source software, and they are somehow open boxes. So we know exactly what is inside the digital twin, and the problem becomes how do I connect the physical with the digital twin? So which data do I want to transfer between the two in order to have accuracy? However, why not asking the vendors themselves, for example, to build their own digital twins? For example, if I buy a router and I want the digital twin, the most accurate digital twin can be built by the producer, because it knows exactly how that device will operate. So I think there will be space also for the capability, the possibility, if you want, for vendors, for producers of services to define their own digital twins, because those digital twins could be different from the one that I presented. They could be black boxes, in the sense that for a digital twin to be effective, it does not need to be a white box. So you don't need to know exactly what is inside. You only need this digital twin to be a real-time and accurate representation of the physical counterpart. So discussing with some colleagues, we found an advantage of this approach, because we could use digital twins to protect privacy or, for example, secreted information, because this can be embedded in the digital twin, and it's not to be disclosed, because I can predict the performance, I can analyze what-if scenarios, just if the digital twin is capable of reproducing the real system. I don't need to know how it works, but I need to have the same functionality, so the same input-output, if you want. So this can be, in my opinion, something that is not very popularly described, but it can be a good point, because typically a company doesn't want to disclose all its secrets, let's say, and through digital twins, they could still maintain them closed while providing a useful service for automation, for example. So I can have a digital replica of my system without requiring to know exactly how it is implemented. I will know that it has a specific level of accuracy, for example. So how do we move forward, and how I go to closing, let's say, this presentation? I think that one of the first applications of network digital twins will happen in 6G. In 6G, there are already white papers and some architectural works that already outline the need to have efficient automation, especially in the network management part. And in several of those, there is already the mention that network digital twins might be one of the components that is used. So I believe that in 6G, we will see probably some integrations of network digital twins already. In general, I think that digital twins, especially of networks, will be useful for training AI and machine learning, because they can generate an infinite set of data sets, an infinite number of data sets, and they can do it very fast, and they can do it in an accurate way if the digital twin is well developed and properly tuned. Another application of digital twins will be modeling and prediction, of course, so to help to understand what might happen in the system, for example, to predict a fault, to predict an attack, to predict the behavior of the users, and so on, because, again, they have a real-time knowledge about the system. And finally, as I mentioned, there will be probably different kinds of digital twins. Here I call them black box against white box, in the sense that I can have open digital twins that everyone can modify and recompile, repackage, and so on, but also black boxes, because the important thing of the digital twin is the interface. So how to interface with the digital twin, and what is the output that I get from the digital twin. And this leads me to another important topic, that is standardization, because if network digital twins will become a key component in future networks, then we need standardized architecture and standardized interfaces to support it. And in this field, standardization is already quite active. Here I'm mentioning a few that I'm aware of. So personally, I contribute to the ETSI ENI, Experiential Networked Intelligence Working Group, where we wrote a white paper describing how network digital twins can provide different levels of network automation in future networks. And also, there is another important relevant working group of ETSI, that is the Zero Touch Service Management, that is ZSM. Here we are preparing with Telefonica and University of Catalonia a proof of concept to show the first example that I presented today. So the usage of network digital twin to predict and react to attacks. But also in the IETF, IIRTF, there are working groups, like there is the Internet Research Task Force on Digital Twin Network Concepts and Reference Architecture, that where I took the graph on the right, that is studying how the digital twins can be positioned. In this case, the digital twin is in the middle, the network digital twin, and how they interact with management and other kind of optimization applications. So there is several working groups that believe in this technology, and they are making the networks ready for integrating this new technology. So in conclusion, I hope that I provided you my view about why it's useful to work on network digital twins, especially for future networks. And I also tried to show you some practical examples, some real examples, because as I mentioned, there is a lot of enthusiasm around this subject, but not many results are available. Especially, I think the network digital twins are one of those subjects that are very good for research, especially because there is not much, let's say, formal environments, or let's say there is not much theory around. I mean, I said that most works are theoretical, but theoretical in the sense about the idea. But there needs to be a theory that helps us to understand how a digital twin operates, which data we should give to the digital twin of the network in order to achieve a given accuracy, for example. So there are links to semantic communications, to internet-based networks, and to other information theory also concepts that are still to be explored. So personally, I think that the results are promising. So network digital twins might be a feasible technology to implement in future networks. Of course, they come with pros and cons that we can also discuss in a minute in the Q&A. So I'd say that it's a good topic for research and also standardization. And finally, I think it's one of those subjects that can bring easily together research from academia with the industrial research, because it's a subject that helps to bridge the gap between, let's say, academics and engineers, if you want, network engineers, because all the subjects and all the angles are required to really build an appropriate and accurate digital twin. So with this, I conclude the presentation. I thank Restart, that is our national project on telecommunication that helped me to develop some of the examples that I presented. And I'm available for questions.
So thank you very much, Fabrizio. Now we'll open up for questions. People who are watching on YouTube can ask questions in the chat. But since we have this delay, Nelson has raised his hand. So do you have a question, Nelson?
Yes, thank you, Fabrizio, for the seminar about digital twin. Digital twin has been a topic of increasing interest here in the project, in our project. So what kind of, especially related to IoT, people are more interested in IoT. So what kind of advice would you give for those newcomers to the field?
Okay, thanks for the question. So let me say a few words about the link between digital twins and IoT. So today I spoke about network digital twins because my area is networks. So in networks, digital twins are more new, let's say, so they are less explored. In other areas, they are already popular, let's say, and they have a very tight link with IoT, because if I go back quickly, let me go to the beginning, a few slides like here. Basically, the digital twin is one of the, in my opinion, one of the most exciting applications of IoT itself, because as you can see in this diagram, it's very important to have accurate synchronization and real-time updates. So those, of course, in a real system, like in a car or in a city, in a field that you use for building crops, for example, they come from sensors. So somehow the digital twin is a service that is built on top of IoT. This is more it's more, let's say, visible in manufacturing, for example. So in manufacturing, you build a system, and if you want to have a digital twin, you need to put sensors in the physical system so that you can transfer the state of the real system into the digital version. Because, for example, you want to know the temperature of the device, whether it's moving, if there are vibrations, and so on, because with your models, you can estimate the failure, for example. So I think that for people working in IoT, the digital twin is, in general, as a general technology, is very interesting. And especially, it impacts, if you want, on one side, on the fact that you need a proper IoT infrastructure in order to enable this, in theory, bidirectional communication between physical and digital version. While in the case of the network digital twin, I think that what is really missing today is more to understand which kind of sensors we need in the network. So it's not maybe the more, let's say, the more wide IoT area, but in the network digital twin, the problem is to understand which data we need to move from the physical to the digital twin. Because, for example, in some cases, you move the traffic, you can copy the traffic or model the traffic from the physical to the digital version, but maybe you need also the information about the state of the buffers in a router, or what the users are doing. So it extends somehow the concept of IoT sensor, but I think the same concepts of IoT are directly applicable to networks, more in the sense of maybe semantics of the data that you acquire. So it's important to understand in a digital twin, not just to have a flow of data without, let's say, specific reasons, but to understand which kind of data you need to exchange. So that, I think, is more, if you want, an IoT, I see it more as an IoT research activity on semantics of the data that you acquire with IoT and how you handle them. But for sure, they are very deeply linked.
Thank you.
So thank you for this, your explanation. I've been working with IoT as well, and this is something that is very interesting to me. We have some questions both in the chat, in the YouTube, and here. I'll go to YouTube. There is a question from Arthur. He's asking, when synchronizing the digital twin with the physical twin, is it done with a full reset, or does it only sync specific parameters? Like they synchronize entirely, or just some specific points of contact, I'd say.
Okay, yes. At the moment, it's a very good question. At the moment, there is a very few works that I find of the two that are working on that aspect, because it's really tricky. I can tell you what we are doing now. So at the moment, we are experimenting with different approaches. In most cases, the idea is to replicate either traffic flow or the traffic. So either the packet themselves, or to replicate the behavior, let's say the general statistics of the packets that are in the different links of the network. So it means that we are in the first scenario that you are mentioning, that is a complete, let's say, backup, but we don't reset the system every time we receive new data. So what we do is we periodically transmit the data between the physical and the digital twin, but we don't play back the data, but we use the new data in order to correct our estimate. So what we do is, for example, we take 1 minute of traffic, we replicate it to start, then we try to estimate what happens in the next 2-3 minutes. As soon as I get a new minute of data, I will use this PID controller that I presented before in order to correct our estimate. So we do something actually in the middle. We don't actually reuse all the data that we receive, but we use the data for training somehow continuously our predictions of the future. But of course, another thing that we want to explore, but we don't have yet results, is to transmit, for example, only a difference. Like if I know which is the prediction, I could transmit the difference, or let's say less information. This is quite tricky because in reality it's difficult to really synchronize the digital with the physical twin. So it's difficult to know how to align the time of the digital twin with the time of the physical twin, with the real time, let's say. But of course, both solutions are possible. What I just can tell you is that the first option that you said, it works. The second, we need still to work it out.
Okay, thank you very much. Now we have a question here from inside our room here. Our colleague, Professor Flávia Delicato, she wrote in the chat, she says, my research group works with the concept of digital twins that emphasizes the feedback loop. That is, changes made in the digital world are reflected in the physical world through actuation operations. Do you plan to address this as well? For example, a decision to change the network configuration that is predicted to be necessary in the digital world could be implemented automatically and synchronously in the physical world?
Yes, that is also another very good question. I didn't have time to get into that, but I mentioned it just while I was discussing about the other direction. So I started speaking about the problem of sending the data from physical to the digital twin. But as I mentioned, and as my colleague correctly mentioned, there is also the other direction. So there is a direction from the digital world, from the digital twin, back to the physical world. And yes, we are doing it now, but I didn't have, let's say, stable results at the moment to show. But we are closing the loop actually. So we are allowing, if we do a change in the digital twin, to be replicated into the physical twin. Somehow it is done in this project already, because the loop that is here in the bottom, it's not directly done because here we have policies and a lot of other intermediate modules, but somehow we are doing it in this project because when a mitigation action is selected, this mitigation action is tested in the digital twin, and if it works, then this action is implemented in the physical twin. So we are doing it a little bit, but not directly as a link between the two twins. So there are in the middle a few policy verification and consistency verifications before going to the action. But we are going also in that direction, yes.
Yeah, and this is something that always I'm curious about because how much automation do we need, or how much automation is it possible to get? You see that if you do like full automation, you could do some damage. This is why like the intrusion detection systems, they don't configure like firewall and other the network security components automatically, because there is a potential for damage. So what do you think about this?
Yeah, that is, in fact, I think that is one benefit of having the digital twin of the network, because, of course, in all the loops, the operations that are more serious on the infrastructure should be, let's say, monitored by the network manager himself or herself. So, of course, we cannot automate everything. But in the case of this project, we actually we are addressing that problem, because we are using the digital twin that is quite accurate for a private 5G network. And we test, for example, firewalling rules or other kind of modification in the setup of the system. We test it on the digital twin before releasing them to the next modules that will define whether the policy is correct, of course, because the network manager can tell that some kind of actions cannot be done automatically. But somehow the network digital twin, I think in this case, helps to make to go one step further in the automation of the system, because it allows at least to filter out actions that might be dangerous. So you can have a more precise estimate of whether an action that you are doing against a threat will damage, for example, the quality of service of the users. So then, if that is true, we don't do maybe that action, but we just alert the network manager.
Yeah, and that might be a case for like not synchronizing everything, because the digital twin could do some simulations just to understand what would happen, or the questions of the type "what if," as you mentioned. And so yeah. We have another question here from Denner. He's asking, like, you mentioned digital twins can generate infinite synthetic data for machine learning. What are the main challenges in ensuring this data is realistic and diverse enough for critical applications?
Yeah, that is a good question. I think that in principle, yes, we can generate infinite data. Of course, as in all generative approaches, actually there is the risk to generate, let's say, repetitions or somehow, let's say, artifacts that maybe are not real. That is why I think that the best way to operate is, I mean, the reason for using the digital twin and not just generating data is that with the digital twin, you start, if you can do the digital twin well, that is the point that is still a little bit pending, because no one at the moment can tell you which is the accuracy of a digital twin in principle. So it's still under debate. But the way to generate data, in our opinion, is by augmentation. So you use the digital twin to have a realistic replica of your scenario that is based on real data. So you need some real data, because otherwise it's not a digital twin, of course. And then you augment the data by using still the digital twin concept. So what you learn from the data that you have, you apply it to generate, for example, more people in the scene or a different angle. And to tell you the truth, I think that it might be enough. Of course, not for infinite amount, but for a long, for a big amount of data, because today, in a lot of cases, as I showed you in the picture, maybe it was not the most, let's say, precise replica of people, but for example, in 3D, we have very realistic ways to render the data, also for movement of people and behavior of crowds and so on. So if you have the proper modeling data and you use the real digital twin data for learning and for replicating similar scenarios, it is plausible to at least generate more data. Maybe infinite, I was a little bit optimistic, but just to make the point. So I'm there is an advantage is that also you don't need to generate data automatically, but you might use again the idea of the what if scenario for generating data. Because, for example, I have some colleagues in Italy that want to study the usage of drones, also visual detection via drones for wild animals. And it's very difficult to have a real life footage of some animals because they are shy, they are small, they move maybe in the trees and so on. So with the digital twin, what we can do is we can generate situations that maybe are very difficult to replicate, to help the system also get ready for situations that we didn't have yet, but built in a realistic fashion. So I think to finish, to close the question, I think there are possibilities to get quite a relevant amount of data. Of course, it will be approximated, but if the digital twin is good, also the data generated will be fairly reliable, in my opinion.
Okay, thank you. We just happen to have another question here. Okay, Marcelo is asking this question. We have been generating synthetic data using GANs, generative adversarial networks. What's the relationship between GANs and digital twins? And I'll take the opportunity to broaden a little bit this question because I've been curious about, like, you mentioned the use of digital twins for 6G networks, and for 6G people have been talking about like AI native 6G networks. So AI might be the center of network decisions, and then you have like the digital twin. The question is, what is the relationship of, like, the AI is inside the digital twin? The digital twin basically is an AI powered component, or how do you see this relationship?
Yeah, that is a good question. The short answer is that, in my opinion, the digital twin will be one of the tools that AI will use, because the more straightforward way to use AI in future networks is to use the digital twin as a mirror. Like when you put yourself in front of the mirror is a tool that allows ourselves to be self-aware, because we don't know how the other people see ourselves, because we see just from our point of view. When we are in front of the mirror, we see ourselves from a different point of view, and especially we see all our body. Okay, so I think that the network digital twin will be useful for AI as a way to better know the network, because then the AI will be able to play in the sandbox, let's say, so with the digital twin, to learn from the network, so to understand both the real state but also the history of the network, because the digital twin is also somehow a big repository of data, because it collects data in a centralized fashion. So it would be, in my opinion, crucial for AI to learn what the network is doing, where the network is going. So this is the short answer. In the longer answer, more, let's say, detailed answer, of course, digital twins also integrate AI themselves. So somehow in 6G we will have probably digital twins for AI, in the sense that the digital twins will provide information to AI for taking decisions, for example, or for testing or for learning. But also we will have AI for digital twins, because probably inside the digital twins already we will have AI either for modeling, because some people are, and this answers also the specific question. Some people can use some adversarial networks, for example, some generative adversarial networks for building some functionalities of the digital twin. For example, estimating the impact of some actions, because maybe this can help to generalize. So my answer is it will be both. Digital twins will be both a tool for AI to play with, but also they will be based on AI. So they will be AI native themselves, but also a module of a bigger set of modules that will be the AI, let's say, ecosystem somehow.
So thank you very much. I think we have a new question here. So Diogo is asking, like, many have been talking about the agentic AIs, like LLM agents. How can NDTs be used to extend LLM agents to networking domain? So like AI agents, distributed AI agents, how can they integrate to these digital twin networks?
That is a tough question, because at the moment, as I mentioned before, at the moment we don't have yet precise standards about how we can interact with the digital twins. I mean, the one that I presented you were examples of what we built, but they are also different themselves, one from the other. So probably I would say that again, most likely, this I think is independent from using agents or not, but probably with agents it will be more relevant, because agents tend to be more independent, so they work on their own, let's say. Probably, again, the network digital twin will represent also a playground for agents to do or simulate actions on the network without impacting directly on the infrastructure. So they can be, again, the network digital twin can be like a playground for the agents to test their assumptions or to gather data without impacting on the real infrastructure, because otherwise one of the benefits of the digital twin of the network, I think, is also to centralize somehow the data, because today it's very difficult to have a clear vision of the state of the network, and sometimes there are proprietary standards. So somehow the digital twin can also help maybe agents to have a common interface to interact with the replica of the network that is accurate. So probably they will go in this direction. I'm not so expert on the agents AI, so I cannot go too much into details, but I have this impression.
Okay, actually, I was curious because you mentioned like the Internet of Digital Twins, and I was wondering if this would have something, some relationship with like distributed AI agents, or how this Internet of Digital Twins could look like, So yeah.
And that is I mean, the term itself, Internet of Digital Twins or Internet of Digital Twins, is already looking a lot in the future. So it's very difficult to say. I mean, maybe I'm simplistic on this, but I have the impression that somehow, at least how we implemented the digital twins in this system, in this project on security, maybe digital twins will become like network functions. So, virtual machines or network functions. So there will be probably modules more similar to web services, let's say, somehow. Of course, here I don't want to touch the security. Of course, there are a lot of challenges in the security then, but I have the impression that somehow the Internet of Digital Twins can be like a sort of NFV, network function virtualization, distributed across the internet. So like, a sort of virtualized world. But who knows? I mean, that is at the moment very difficult to estimate. Maybe it will become a different story. I mean, because some people, the reason why I think they labeled this term Internet of Digital Twins is that if we don't consider the net of digital twins, but more the digital twin of people, of objects, then some people links this to the metaverse, to the concept, of the metaverse. So to have a sort of environment where everything is virtual, but is connected to the real world too. And the digital twins are exactly this kind of interface, because they are both digital, but they are connected to physical systems. So they are somehow interfaces with the metaverse, if you want. So I think that was the vision, but I'm not fully sure which will be the direction.
Yeah, I couldn't refrain myself from thinking that the Internet of Digital Twins might be the matrix for the things,
Yeah, something like that.
Yeah. So, and I think our we are getting to the end of your seminar. I just was curious about, you mentioned that like in the Internet Research Task Force, there is this draft network digital twin concept and reference architecture. So I'm really curious about that. So have you been involved with that, or and which actually research group from IRTF does this draft belongs to? I couldn't really.
To tell you the truth, I'm more involved in Etsy at the moment. But I can, if you wish, I can. I think the group is this one is NMRG. I think it's Network Management Research Group. I think.
Okay. Yeah. Okay. Now I thought.
I'm not directly. Yeah, I'm not directly working on that. I have some colleagues from Telefonica that are involved in this. I'm more in Etsy. We contribute in that one, not yet at the moment.
Yeah, and you see, the last version of this draft is number 11, and it's only from like 2 days ago. So this thing is going on, So it's maybe it will become an RFC soon. At least it looks like.
Yeah, there is a lot of interest. I mean, as I told you, it's a topic that requires interfaces. So there are a lot of push, especially companies are very interested in digital twins in general, and the mobile operators or the telcos are interested more in the network digital twin. Sometimes, by the way, they use this. I typically say network digital twin, but in IRTF they say digital twin network. So both terms are at the moment valid.
Yeah, digital twin network. It means like a network of digital twins is more like the internet of digital twins, or not. I don't. So I have to read the draft to
No,
understand.
I think that they mean the same that when I say network digital twin, because if you see the diagram, there is it's connected with the network management, so it's I think it's the digital twin of the network. But I don't know why they wrote it in this way, to tell you the truth.
Okay, so thank you for this
My pleasure.
exchange of ideas. So we have just a final question here from Arthur again. He is asking, you mentioned that it was hard to know if the digital twin is a good representation of the physical twin. Do we have any guidelines in how to measure the fidelity of the digital twin?
That is a very good question. I think that again there is a short answer and there is a long answer. The short answer is let's say, given an application, of course you can evaluate the accuracy. So if I use the digital twin, for example, to predict attacks, I could study in different situations, like when you do simulations, so you can study the probability that you detected correctly the attack, and that can be your accuracy. The problem with digital twins of networks is that a priori, maybe you don't know exactly how you will use the network digital twin, in the sense that maybe you want to detect attacks, but maybe you want to detect anomaly or something different. So the long answer is there is still work to do. So I believe that I mean I'm not very good in information theory myself, but I believe that people expert in information theory and semantic communications can find some interesting framework to study digital twins, because at the end the problem of network digital twins is more semantic. So can we have a replica that behaves in the same way as the original system? And that is more, let's say, semantic problem. So does it do the same stuff or not? Because at the end we don't care if one packet is it loses maybe one packet more than the real system, but we need to have something reliable also. So it's an open question. I think the question is good, but it's open. To the best of my knowledge, no one still did this. I would like to, but I need some expert in information theory.
Okay, uh, thank you very much. I think we don't have more questions, and we are running out of time here. So if you don't have more questions, then just open up for you if you want to say some final words about the subject, and then we can finish our seminar in the transmission. Okay.
Okay, so from my side, thank you very much for listening to the presentation. I hope that I opened some interesting topic for you. So I'm available also offline. If you have any questions, you have my email. I will also send to Nelson the PDF so he can share with you the presentation.
Okay, so I'd like to thank once more Professor Fabrizio Granelli, and also to thank everyone who joined us here in the room, and also by YouTube, and also to thank the ones who will watch the video later on, because these days um, most people watch the videos later on, and they just accelerate like two times. That this is very common. But we had basically like 70 visualizations, which is really very good. Uh, and then I just like to say that our next seminar will be in 3 weeks, in the end of July. So thank you and bye bye, and see you in our next seminar. Bye bye, Fabrizio. Bye bye, Nelson. I will
Thank
end.
you. Thank you,
Thank
Fabrizio.
you. Bye bye. Thank you all.
Okay.